Thank you very much. Thank you, Mark, for that kind introduction. Good afternoon. As noted, my name is Naoko Ellis. I'm a professor in chemical engineering at UBC, and I have been looking so forward to this opportunity. I became a faculty associate very quietly at the beginning of the pandemic. So it's like, well, I'm here, but I wasn't able to connect with you. So here I am, and I'm delighted that there are a bunch on Zoom as well. So thanks for coming. And I think I'm going to start. If I could, ooh, we did. Oh, good. Okay. So I'm going to start with this image. This is my class back in September when it was a little bit nicer weather there. And we acknowledge that we're on the traditional, ancestral, and unceded territory of the Musqueam people. And through this class, we're engaging, and these are engineers, engaging in what that means. So thinking around what that means and what kind of responsibility we may have. So with that, oops. Okay, this is a little clunky in terms of thing, but when I was preparing for this talk, this image really spoke to me as in terms of, I know where I'm going, but the path has been pretty tortuous and meandering. And so for today, I'll talk a little bit about my research area, then move on to carbon management. And if I could get my slide to, oopsie, okay. So this has happened before, but okay, carbon management. And by the end of the talk, you should know what CCUS stands for. And then to close off, I'm talking a little bit about my current projects, including the transdisciplinary research. So just to get us warmed up, because I have another question down a little bit later, but my research area is in fluid particle interactions. And if I were to ask you, if you could think of an example of a fluid particle interaction, what would that be? And so just as a warm up, I'm gonna hope that those on Zoom could put it in the chat. And those who are here, here's the question again. It's flickering. Yes. What are some examples of fluid particle interactions that you can think of? Let's hear it from you. Anything? Thank you. CO2 in the atmosphere. Now, CO2 in the atmosphere is gaseous, so we need to have, let's say, a human, having interaction with that CO2. And is it flickering for you as well? This is most unfortunate. I'm not doing anything. Okay, well, bear with me. So one that I thought of was popcorn. And in fact, this was on my final exam where the kernel was suspended by hot air and it pops, and sort of talking about velocity and whatnot. Skydiving is another example where human would be the particle and interacting with that fluid. What does that have to do with my research? So if you were to take a look at my lab, it might look something like this, where I may have a container full of sand or beads, glass beads, and I have holes at the bottom of this vessel in injecting water or gas. And if I could put in enough gas through it, these particles that are just happily sitting there starts to move around because it's being suspended. And that's at the stage where I would see many things, including something like this, where it would act as if it were fluid. And that's the term, thus the term fluidization. I won't get into that, but my research area really looks at these interactions and understanding how this may be. So to give you two examples of my current and application of that is biomass gasification. We're sort of looking at wood chips or sawdust, and that is exposed to air or nitrogen. And we are heating that up in order to get syngas, which is hydrogen and carbon monoxide. That is basically what's happening at the NextEra. unit on campus through the Bioenergy Research and Demonstration Facility, BRDF, and whereby these wood chips are being gasified and taken so that we could generate hot water to heat the rest of the campus. So that's one project. The next one would be to do with carbon capture, which is using lime, calcium oxide, and reacting with CO2 to make limestone or calcium carbonate. And that is in the form of carbon capture that I'm involved in as well. So at this point, I want to sort of step back and take a look at the regional strategy in mitigating GHG emissions and getting to 2050. And this is a little awkward because I'm trying to point at things, but I guess the Zoom folks won't be able to see. Annotation might be good. Let's take a look at if I am successful with this. Oh, nope, deny. Okay, never mind. This is the life of us this term in teaching hybrid. Okay. So here we have different sectors, and year is 2010 to 2050. And assuming that we're going to electrify cars and trucks, that GHG contribution from that is minimal at this point. Through buildings, it will be retrofitting as well as changing the building code to make it less in terms of the GHG emissions. It does not go down to zero, and so on and so forth. What I want you to sort of take a look at are the bottom two green ones, one of which is ecological carbon removal, which is including forest and bog and different coastal ecosystems that will take up CO2. And that's considered here. And this is below zero, which is basically negative carbon scheme. And the bottom most green one is the technological or engineered carbon removal, which is dealing with carbon capture and storage. And so at the end of 2050, we hope to be net zero carbon GHG emissions. And so this positive emissions are counterbalanced by the negative of this green. And that's the scheme that we're sort of working towards. So just a few slides to talk about carbon capture and the gist of this. Basically what we're looking at, if I were to represent these gas molecules, blue ones in CO2, yellow ones in nitrogen, and I have a carbon capture device, let's say this black, the box, and the box would have these receptors, which have affinity to CO2 molecules. What basically happens is the stream that goes into the carbon capture device, and CO2 gets bound to these receptors, and out comes pure nitrogen. And at the end of it, when all these receptors are saturated, then we put in some energy to release that CO2 so that we now have fairly high purity CO2 stream coming out. So basically, when you think of carbon capture, it is really to do with dealing with a gas separation unit. You'll have a stream come through, and then you'll have two different streams that will come out from this unit. Couple things to take note. Not all sources that contain CO2 are the same. And one of the significant one is the concentration of CO2. So if I were to think about capturing CO2 from, let's say, boiler stack, where CO2 concentration may be around 4 to 13%, that would be very different from trying to capture CO2 from air, which is, I'm going to ask the students what the concentration of CO2 in percentage may be. 0.04-ish, 5-ish%. And so that's a tremendous difference in energy that is required. And that's basically governed by thermodynamics. It is to do with the probability that these CO2 molecules do get attached to the receptors. And so this, which is depicted as 50% CO2, and this, which is much less CO2, the energy required to capture CO2 is going to be very different. So that's one takeaway. Another takeaway is that once we have a saturated CO2 receptors, we do need to let that CO2 go, release, or we call it regenerate. And the energy that's required to that really depends on how CO2 is bound to this material. And so that makes a difference as well. At the end of the day, what we're trying to do is separating is fine, but we do need to have utilization or sequestration schemes. So once you have captured your CO2, we might actually be able to use that. So in this case, it's calcium carbonate, use it for building material in different ways of utilization. Another way is to have pure CO2 be stored in geological formations where you could see, I'm not sure if you could see this, but the white part in that scheme is basically carbonates that are being deposited and formed. So CO2 is turning into a part of a stone underground. So now we know what carbon capture utilization and sequestration is something that we have been looking at. A couple examples of that. Canada leads in that we've been the first to commercialize carbon capture attached to a coal-fired power plant and Sask Power Boundary Dam. And we could see that they've been capturing 1 million tons of CO2 a year, and the power output of this from the whole plant have reduced as a result from 139 to 110. And you can see that this big building over here is the power plant part, and this is the amine capture, CO2 capture component. Once pure CO2 is generated, it is taken down on a pipeline and it's being injected underground, a kilometer or two underground. And it was surprising to see how small the wellhead was in relation to how large the operations are. For this system, we use something in terms of receptors. We use amine, and that binds or reacts with CO2 to form carbamate. And this scheme is called chemisorption, and it does, relatively speaking, take a lot of energy to then release that CO2 once it's saturated. Thus, the energy penalty that we're seeing from the power plant. Next example is by Savante, and this is an interesting one where it has a structured film that is in the rotating bed. And so for number one is where this bed is capturing CO2 or the flue gas is going through. And then the bed rotates over to where this goes to number two. It's met with steam, and then CO2 is released at a pure form. For this, they've been using something a little bit different than amine, and these are called metal organic frameworks, which are chemical compounds that physically kind of binds the CO2 inside. So what we're seeing here is a cage-like structure with CO2 molecules inside. And what this allows us to do, which is basically a physisorption mechanism, is that CO2 to be released, when wanting it to be released, it requires less energy than the chemisorption part. Lastly, this is the example that we have for on campus. We are installing the Clean O2 system, which is, they call it a mini or micro CO2 capture system. And it's basically retrofitting this to a boiler or hot water system by having the flue gas go through this unit here. And it's binding with potassium hydroxide and generating potassium carbonate. And that's a powder that is generated. And once you have enough powder, you take that away. And they are currently marketing as making soap and marketing that. This unit has been installed maybe 10 or so in BC. And that's, yeah, we'll soon have, we are able maybe to do a UBC brand soap if that's something, some interest there. So overall, we sort of then think about, well, what are some of the costs associated with this? On the left-hand side, you have a list of ways in which you can capture CO2. The top is basically, x-axis is the US dollar per ton. And what you see are the light blue bars representing low, capturing CO2 from low CO2 concentration schemes. So direct air capture is requiring a lot of energy, therefore a lot of cost associated with it, versus darker blue bars are showing that it is much less costly. And this is mostly representing the operating costs of these units. Knowing that Canadian government is looking at $175 a ton on carbon tax, well, what would that mean? In today's exchange, that will be around 140 US dollars a ton. And sort of this gives us a good sense of what might be possible in terms of CO2 capture. And in a grand scheme of things, we're sort of looking at many different scenarios in terms of capturing CO2. Bless you. So we have these power plants that may emit CO2, which we may be able to capture. It can be going into a injection site or chemical plant that uses CO2 as a source for further processing. We also have the scheme, and you can't see it at the top there, but basically having forest, so biomass CO2 removal, as well as air capture is shown in here. So there are a number of ways in which we could think about how CO2 may be captured and utilized. Oops, I touched that, so I jinxed it. This is just a plug for those students who may be looking at an additional technical elective course. I am hiding that URL, so I'm going to move that away, but there it is. If you're interested, check us out. We offer a course on this. So at this point, I'd like to sort of pose a question to the audience, including those on Zoom. Why are these technologies not becoming solutions yet? What do you think in terms of the barriers for adopting CCUS? And I'll pause for a moment and see if I could garner some responses. And even not, if you are able to put into the chat, it'll give me later on a good sort of sense of the sort of the perception that you may have. So this is a good info for us. So yeah. Yeah, so what I'm hearing is basically the challenge of transporting CO2 once we capture. How do we deal with that? Absolutely. That's a huge challenge, and that's going to come up a bit later, but thank you for that. Anything else? I mean, it seems plausible that we can deploy these kind of technologies. Why are we talking more, I wonder? Yep.
Related to large-scale implementation, just how fast it is, how big it would have to be to tackle.
Yeah, that's another point, because any large scale, the first example that I had for Boundary Dam, that took years to build. And so, yes, companies may be thinking about getting some engineering sources to build or design a unit, but it'll take 5-10 years to build. Thank you. Yeah. Any other? Yep. Yeah, so where the CO2 is being emitted versus where it needs to be stored if we are to store. Yeah, absolutely. And that sort of comes back to that transportation issue as well. So that, and I guess the related cost could also be that. Well, thank you. Thanks for those points. Okay, so with that, I'm going to switch gears to talk a little bit, and I'll come back to this, but switch gears a little bit in terms of my sort of thinking how it evolved around this. And of course, I'm in the business of educating or training engineers. And we've been talking a lot about, we do talk a lot about technologies and whatnot. But more recently, I've been sort of thinking around, why aren't we making progress? Why aren't these technologies becoming solutions in society? And that's got me thinking around, well, we do need to understand not just engineering material, but really have a meaningful dialogue and conversations with those in policy, economics, really understanding the leverage points and how system works. And so with that in mind, what we did was in 2017, we got some funding from UBC Killam Connection and provided or set up a graduate course where it was taught by these wonderful people here that are familiar to this audience, I believe, but really bringing together some courses and public lectures around leading the way towards a low carbon future. And listening to my graduate student who has taken this, who is trained as an engineer, and she now works for City of Vancouver, but this course did give her a really diverse perspectives and understanding of how technology is looked at in the context of where it might be implemented. So with that, this is one of the examples of the public lecture we had, and we had about 5 of these, and having really diverse perspectives on getting to low carbon future. So after that experience, and it was a positive experience for many of us involved, we were also starting to look at, well, what more do we need? And more I've been thinking around, it's not just bringing those disciplines together, but really to tackle complex issues that we're faced with. We need to start thinking around the emergence and the way in which we may come up with a new way, new perspective of looking at these challenges. And so it's not necessarily a disciplinary identity that is there, but collectively, can we actually see things and ask questions to get to solutions in a different manner? And so with that in mind, we got some seed funding from the UBC Climate Emergency Fund. And current members are this, and I'm really inviting those faculty members who may be interested in joining to let us know. And what we're doing is to build a transdisciplinary collaborative PhD student cohort starting in the fall of 2022. And so this is really to grapple with some of those things around what would it take, and we will be accepting students. Melinda's going to be leading that recruitment, but accepting students from diverse backgrounds and really having that cohort experience to think about these, particularly under the umbrella of climate emergency. Leading up to that, we'll host a co-design sort of 6-month period starting in January. You might have gotten an ad on that, and we'll be working, faculty will be working collaboratively with students to sort of co-design some parts of this program. And also during that time, we'll be building relationships with stakeholders, and these could be some existing relationships, including industries like pulp and paper, mining, or cement, different government organizations that we'll be engaged with. So lastly, I only have 2 slides, and this is my latest project that I'm working on, is really kind of stepping back again, but looking at the CO2 emissions. And sort of this is a graph or map that was put together by a colleague of mine over in Natural Resources Canada. And these bubbles are representing different sources of CO2. The size is representing the emission rates, and looking at across Canada to see where are we having these emissions, what are the strategies to think about how to capture and store. And so BC is something that we're looking at. You see many green and blue biogenic emissions by having biomass being combusted in kilns, in pulp mills and in mining area. And looking a little bit closer to that, here's a conceptual sort of transport infrastructure. And I say this a little bit quietly and carefully, but let's untangle this a little bit. So on the right-hand side, you see a lot of green lines. Those are the existing pipelines in Alberta. And as you can see, BC, the green lines are sparse. Actually, the storage site that we have so far are in the northeastern part of BC, as well as the southwestern part of Alberta. So that in itself, you have raised those points, but in itself is a challenge. And what does that mean? So how do we actually start to think about how to grapple with this kind of problem? And the orange line is a conceptual pipeline. And I'm thinking, who needs to be there? How do we actually even start to engage in a dialogue and having that narrative push forward that we could all agree or be comfortable with? And those are really challenging steps that we need to think about. And these are some of the areas that I'm working on at the moment. So with that, I'd like to conclude. I guess fluid particle interactions are everywhere is one takeaway perhaps. But in terms of carbon capture, yes, the source concentration or the energy requirement needs to be considered. And in terms of CCUS, I hope I did give you enough example to show that it is a possible in the realm of possibilities. And finally, to invite those to join us in the transdisciplinarity in the research area. So with that, I'll just leave this on as a plug, those students who may be interested in joining, but thank you very much for your attention.
Thank you, Naoko. Yes, we have some questions. I want to ask you a question really quick about different research on
Okay, the emissions on that. Okay, here we go. This one. Oh, others. Okay, so that will be working with natural gas. So when we mine for natural gas, CO2 does come out, and is that emissions that are associated with natural gas processing. It's pretty big, isn't it? Yes. Yeah. Yeah. Well, I'll do my personal. Okay, yes, the question was, okay, sorry about that. Yes, the question was my personal opinion on clean hydrocarbons. Right, okay. My personal opinion is that we can't afford to dig more or bring more hydrocarbons. Now, so the point about direct air capture, I mean, we can do those things, yes, but what are we sacrificing to do that? I'm not for or against that. I'm not saying anything about that, and I want to be super careful around that. But we are using, if we are using that much energy to capture CO2 from air, could that energy be utilized differently? Would that have been a scheme? So that's a conversation we have to have. Now, from the research perspective, we do need to do everything. So we do need to understand how we might improve air capture in terms of, different chemical species and whatnot. And so that's that. But when it comes to adopting into the society, we do need to think about systems and making sure that we are okay with, I mean, we have to compromise something. So we're going to have those difficult discussions to really direct this, navigate this space. Yeah, thank you for that tough question. Yes.
Thanks a lot. I'm super excited about this idea of like a transdisciplinary approach.
Mhm.
And I wanted to ask a little bit more about you all are kind of conceptualizing transdisciplinary as opposed to like interdisciplinary work. And especially in kind of, well, first, how you define transdisciplinary, okay? And then what are some of the challenges that you've had in terms of trying to keep those
Yeah.
goals? Yeah, or what you foresee as
Yeah. Thank you for that question. So the question is around transdisciplinarity, collaborative PhD. What are some of the definitions of transdisciplinary research versus inter or multidisciplinary? And Lillian's going to help me with that, of course. This is why I invited you. No, I'm kidding. But yes, we have already, well, we've been really having some rich conversations with those folks that you've seen. And in terms of multi, inter versus transdisciplinary research, we're sort of looking at what are the ways, the new ways in which we're going to be able to generate questions and perspectives, epistemologies, those are ontologies, all of that is new, as opposed to having a multidisciplinary and I'm having an engineering sat and somebody else is bringing in that economics perspective and coming up with something that are like in the Venn diagram, cross-disciplinary. And so the transdisciplinary is really exciting to me in a sense that we might be able to ask different kinds of questions that may lead to different ways of solving it. Now, feel free to add to whatever I'm saying. In terms of challenges, it's difficult because we're saying, we don't know what kind of projects we're going to be working, but we're going to have students come in. So I think what we're sort of trying to do, because funders will not fund, well, the blue sky, you say you're going to tackle the climate emergency without telling them what we're exactly trying to do. And so that's been a challenge in terms of acquiring funding. But what we are starting to think about is to take that first year, which we have funding for, and have students go on internships and spend a good chunk of time in different stakeholders and understand their perspective and how they're grappling with climate emergency. Could we have those students come back and really think about and generate something that we might be now? Each student will have to have their degree. So that's another, we have to make sure that they become in their disciplines, in some ways, an expert in an area. However, there will be some co-creation of a part of a thesis or maybe something that they work on. And having that discussion is hopefully going to generate some different ideas. This is where I'm at. Lynn, would you like to add in?
I just think about it problem focusing. So that way you're making the problem focus on the analysis and not here's the problem that is expressed by those individuals who want the problem solved as opposed to me sitting in my office trying to think that's a problem solved. That's one part of it. And the second part as well is the problem how do we get comfortable. So my point of view is that.
So I'm going to reiterate what Millen has said, is basically to think of it as a problem-based kind of approach where there is a problem and how do we have students go and understand that problem, I guess, in some ways. Yeah, so that's where we're at. Thank you. It's a great, yeah, it's been a great journey already, and I'm sure we're going to have a lot of fun. Yeah. Yes.
So, like, I've always been a CCS skeptic, I must say, throughout my idea of climate mitigation. But now I'm starting to sort of be dragged into it, kicking and screaming, because I'm starting to see the space for other reductions shrinking,
Mm-hmm.
and this idea of negative emissions technology growing.
Yep.
Right? So that clearly there's a momentum in that direction.
Yep.
That's on the one hand. On the other hand, it seems progress is incredibly slow, right? And it doesn't, I mean, well, some of the engineering problems might have been solved, at least at the capture level.
Mm-hmm.
But the question of, there's still an open question about costs. And there's an open question about what do you do, and its long-term integrity of the story.
Yep.
So what's your thinking about sort of, this seems to me to be something that is almost inevitable, yet it's not moving.
Mm-hmm. Yeah, so I guess I have a vantage point of dealing with lots of small to medium enterprises in this field of providing technology solutions. And I have to say, I'm quite impressed. So I know things are there. And that's my kind of a message. Oh, sorry, I did not reiterate your question, but your question was basically around CCUS and its efficacy and reducing the GHG emissions. You're a skeptic, but you think it's a necessary tool to get to 1.5C. So yes, but I am encouraged by the ingenuity from the engineering point of view. There's so many solutions that are coming out. Now, it's not going to be cheap, and it's going to be hard because we've waited a long time. And yes, your point about it seems so slow is valid, because we have never had enough money to really push that forward in some ways. So that's kind of a chicken and an egg. Oh, yes, we needed the carbon tax before to do this type of thing. But things are changing, right? Because BC has had carbon tax. We now have a BRDF, which is using biomass to heat the campus. And so those policy instruments need to be there. It needs to kind of shift our thinking, because it is going to be painful to get to 1.5, I think, regardless. But I believe that it is a possibility. It will start to happen, and we'll start to see a lot more examples. Now, in terms of storage, integrity of storage, there's a lot of research being done in that. And I am not a geologist, so I can't speak, but I am confident that in certain geological formations, it is turning into carbonates, and it is turning it like that's secure. I keep telling my students, engineering students, that eventually there may be an opportunity to bring that CO2 back, because we figured something how we could utilize that as a chemical source. But until then, I think the way to deal with it is to store it geologically for now. Yep.
We have a question from Zoom.
Yes.
They're asking, what's the biggest hurdle you face in switch from being pure engineer to doing transdisciplinary work? What do you see as the biggest barrier to creating collaborations between people across lines?
Thank you for that question. Being an engineer, yeah, I think I've kind of came over, but what's the challenge? I think in one way, funding is a challenge, because funding agencies that are funding me to do carbon capture technical stuff will not be funding me to do transdisciplinary stuff. So that's one challenge. In terms of challenges working with people, I think we all need to be really comfortable with being uncomfortable and unsure. It's interesting because I will go into these meetings with diverse faculty members, and I have to be prepared to not know everything, really kind of be okay to not know it, but to really find ways to communicate, because we ultimately speak different languages in different disciplines. And so those are some of the challenges that I see. But what I'm seeing and hopeful of are seeing students who are really coming together and understanding and just generating different, perhaps a different language even, just to be able to communicate and think together. And that's, to me, is a hopeful sign. Thank you. Yeah.
How do you feel worried that it might have a smoke and idea that those companies are championing in order to get into
Yes, this is a really tough question. It's related to fossil fuel industry and CCUS. I do get requests for write-ups for, are you for or against in terms of fossil fuel industry adopting CCUS, and try to go their way. I think we need to think of it not just from a technical side, but to understand that we need a just transition scheme. And so fossil fuel industries have had this expertise in many different ways. How do we transition that industry into something that is like cleaner, meaning in a different sector? Could that be possible? Those folks that are in working and having expertise in different areas, is there a possibility to retrain so that they might be able to transition to another renewable type of industry? I think we need to start thinking about kind of a holistic societal change way. It's true, like we can't live without fossil fuel right at this moment, but then that doesn't mean, to me, that doesn't mean that we're going to be building an infrastructure to still pump fossil fuel so that we're committed to using that infrastructure. That doesn't make sense to me. But then how do we really grapple with how to transition is something that is really not so simple. And of course, the narrative that comes out from, from different media is really polarizing. And how do we bring together that we are actually on the same team? We have to get there together. So how do we generate that type of narrative in, having these students come out to affect change in that way? I think that's kind of a divergent way of answering your question, tough question, but thank you. Yeah. Yeah. Yeah, so I think if I hear you correctly, we're talking about that last map that I showed with the conceptualized CO2 pipeline. How do they decide? I mean, it's not decided at all, clearly. I mean, I'm at a point, that's not my thing, but I'm at a point where how do we even start to talk about that, right? The question may be where to put that pipeline, not to say that, but to sort of ask, okay, as a BC, these companies are willing to collect or capture CO2. What should we do with that? How are we going to manage that so that we can get to these potential locations? something like that. And that's still like, it really still keeps me awake actually at night thinking about, because it's an enormous, enormous challenge. Initially, what we'll do is to use rail, because these pulp mills that are dispersed in BC are getting chemicals through rail. So the rail may go and deliver chemicals, and afterwards CO2 could be compressed, put on rail, and brought back to where it might go. That's okay to a certain point. And by then, would that still become economical if every 7 minutes there's a rail, train going through? Like, is that even possible? So the challenge is enormous. But yeah, I'm hoping that we have a way to think about it and ask good questions to start to grapple with it. Yeah, thank you for that question. Yeah.
Carbon capture technology, what percentage of the estimate of innovation is driven by governmental funding versus industry?
That's a good question, because there's a lot of funding in this area, like Elon Musk's, carbon challenge. I mean, those are huge. And this is great because I have colleagues that are really at that point where they could scale things up. Now, government is funding clearly the more fundamental research side, and as well as those examples that I've shown, there are funding behind those as well. So, but I'm not sure in terms of the percentage. I'd have to kind of sit down and look at that. Yeah.
I'm wondering if it takes government mandating or policies before there's more commercialization and participation by industry to invest further. Because as I'm watching the slide, I'm kind of echoing what I've heard from the feedback that, it's great technology, but how scalable is it? How economically viable it is? Because, when I was in my industry in the water technology side, you can have the greatest technology, but if it's not commercially viable, it just gets shelved as research.
Okay, so sorry, I didn't repeat that question, but it is to, thank you for, I don't know if you put that question in there, thank you. And so it is about scalability and viability of certain technologies. What it is about CO2 is that every kind of source is different in some ways. And so solutions are quite different as well. And the scale at which it would make sense becomes really different. And so that's a challenge in itself. What we're trying to do with the last project is to have this modeling platform where, as a company, I might say, I have this much CO2 with this kind of concentration, and this is my proximity, and then to put it in to see what kind of technologies are available. And so that's at a federal level they're thinking about. And so that is going to push some of the technology developers to really up their game in having to come up to a viable solution to be able to provide through that. Carbon tax is, and I'm not an expert in this area, but the experts here, but has worked for BC in terms of sort of shifting that thinking and growing certain areas of economy that needed to grow. So I think it is sort of like you try something, learn from it, and then try further down the road. That may be a way to deal with this complexity that we're faced with.
So in your experience, do we have the technology to do this, and we just have to optimize to make them better, more efficient, more cost effective? Or do you think we haven't even scraped the surface of what might work better?
I think we have the technology. The question was around, do we have the technology for this? We do have technologies. I mean, different scale, we do have solutions for different scales. It does need to be demonstrated so that people have confidence that it does actually, work. And that's probably, we're at the cusp of that right now. And there are a number of federal funding that are becoming available to demonstrate at a scale that is, relevant to society. So we'll probably see a lot of that as well. Thank you. Yeah.
What types and in what ways technical research be used to inform policy decisions?
How can technical research inform policy decisions? And I think, what type? Well, I think having to understand its parameters in terms of each technology, understanding the context in which it works, those are all information that is relevant when it comes to making policy, or should be fed into policy. Sorry. Sorry, I'm not following that right now, but yeah. I hope that some of our students who are technically trained will be able to have those positions where they might be able to join that policy decision-making area. And I won't be able to say exactly what type and what format that may look like, but it is vital that number of different types of technology are understood, and some of the limitations is clear in terms of scale and whatnot.
Maybe the follow-up that one last thing you said there is people who have a technical understanding can be involved in the decision process.
Yeah.
So, so do you think it's better to come from a technological background and learn the policy side? Or is it better to come from the policy side and learn the technical background?
Right. So the question was, as a decision maker, would it be better to come from technical background and then move into policy, or vice versa? And this is why I feel like this collaborative PhD is going to be the solution. But either way, right, we bring strength in different ways. And so it's not like we're going to be able to produce a carbon copy from going from different ways. But I think having the diversity and being able to have variety of those folks that come different pathways are going to be important.
Well, sorry to cut this off. I think there's room to have time for one last question, Bonnie. Okay, so why don't we get one last question, and then it's going to really interesting.
Oh, sorry. Okay, I will walk with you to talk about the question, but I'll take one from the Zoom folks.
Based on the previous answer, how confident there are students, carbon capture and utilization, or carbon capture underground technologies to deal with almost every type of emission source. However, there were multiple critics during the COP26 saying that everyone is relying on CCUS when neither the tech nor the biological sinks will be sufficient. Were the critics wrong, and why?
So I can't say that there is a technical solution to every single different types of areas where there's CO2 emissions, nor would it make sense to have CO2 in CCUS in every case that there is a CO2 source. Now, in terms of the COP, can you, sorry, repeat that question?
Just saying that there were critics of this idea during the COP, and they were saying that everyone's relying on CCUS when neither the tech nor the biological things will be sufficient. And so they're wondering, was that critique correct?
Well, if we saw that graph of Metro Vancouver's modeling, it seems like we could get there by 2050, but that really requires us to really start working on it today. Are we committed to that as a society? Are we willing to give up certain things to get there? That's a different kind of conversation. But in terms of technology, I can't say I can't say they were wrong or anything, but I do, if we believe that modeling does work, we should be able to deliver the technologies that are required there. Yeah.
Coach, join me in thanking Dr. Ellis for